Good. So what we're doing in this video is we're going to introduce and work with algebraic fractions. So let's start in this way. So I'm going to write down a binomial. Now let's just start with a quadratic. So let's say something like 2x squared minus 2x plus 3. Keep it nice and straightforward. And I'm going to divide into that, so let's just put a fraction bar here, x plus 1. Now I know that my numerator here is not factorable. It's not straightforwardly factorable anyway. So it's going to produce a remainder when I divide x plus 1 into it. And so that's how we're going to get our fraction. Okay, let's give that a go then. So I'm going to use the let's use synthetic division, since x plus 1 is going to work with synthetic division and it's nice and quick. So I take my second term in the binomial here, the 1, and then I write down my coefficients here, which are 2, minus 2, and 3. Drop down the 2, multiply 1 by the 2, I get 2, put the 2 there. Minus 2 minus 2 gives us minus 4, and then 1 times minus 4 will give us minus 4. 3 minus minus 4 is 3 plus 4, giving us 7, and that 7 I know is the remainder. Okay, so I can then use these two terms here to get the first terms of the answer. So we get the binomial here, which is 2x minus 4. And if you're not sure how I'm doing this, obviously I went through this much more carefully in a previous video, so have a look at that. Okay, now what do we do with this remainder of 7? Well, let's just pause and think for a moment what would happen with conventional numbers. If I had something like, let's see, 35, let's say, so if x equals 10, that would be 3x plus 5. But 35 divided by, well, let's just say 8. So how many times does 8 go into 35? Well, it doesn't go in exactly. So what we end up saying is, well, we can have, let's say, 3 8s, 4 8s would be 32. Yeah, so 32. So it goes in 4 times. So we would say equals 4 and 32. So 3 remainder and 3 remainder. But instead of saying remainder 3, what would we say? We'd write 3 8ths. Okay. So we're very used to with conventional working with conventional fractions like this, saying, well, instead of writing remainder 3, we write the 3 as the numerator, and the denominator of our fraction is the divisor that we use to divide into the 35. So that becomes our denominator. So if that's how it works with ordinary arithmetic, then the same principles of arithmetic apply to algebra. So let's just erase this working out for the moment. Give ourselves a bit more space and compare what we did here to what we're going to do here. Well, the numerator is simply the 7. Okay, and so our fraction will go over here just as with conventional numbers, so plus 7 divided by the denominator, x plus 1, or the divisor if you like, x plus 1. So there's our fraction. So 2x squared minus 2x plus 3 divided by x plus 1 equals 2x minus 4. That, if you like, is our, let's just put square brackets around it. That represents our whole number, just with a variable in it. And our fraction, let's put conventional brackets around it, is 7 divided by x plus 1, or 7 is the numerator and x plus 1 is the denominator. So there we go. There's our algebraic fraction. Let's just do another one just to see how that works. And this time I'm going to let's use a divisor with a coefficient in front of the x. So we've got 3x minus 2. We'll divide into, let's see, something like 3x squared, keep it straightforward, minus 5x minus 3. Let's see how that works out. Okay, so we have to use long division. We can't use synthetic division this time because we don't have a monic term here. We have 3 in front of the x. So we're going to use long division, but no problem, because although it does take a little longer, you can get quite quick at it. And so we'll go through this quite quickly. Okay, 3x into 3x squared will give us x, and I'm going to put my x there. X times 3x gives us 3x squared, and then multiply by the minus 2 gives us minus 2x. So the 3x squared is going to cancel when I subtract. Okay, so now I've got minus 5x minus 2x, going to give us minus 3x. Bring down the minus 3, and off we go again. 3x into minus 3x will give us minus 1. Minus 1 times 3x gives us minus 3x, and multiply the minus 2 as well gives us plus 2. And so now we've got our denominator is minus 3 minus 2, giving us minus 5. Okay, so remainder 5, but here is our whole number. Instead of remainder 5, we're going to say minus 5 over the divisor, which becomes the denominator now in the fraction, 3x minus 2. And I'm going to put my brackets around the sign here, because really we should say this fraction is negative 5 over 3x minus 2. Great, so here are examples of algebraic fractions, and what I'm going to do now is combine them. I could combine all of these answers, but I'm just going to take these fractions and show you how we combine fractions. So we can call this addition, algebraic addition of fractions, and our first algebraic fraction is 7 over x plus 1, and our next one, we can say we're adding, if you like, is minus 5 over 3x minus 2. But because we're adding a negative, makes sense really just to say we're subtracting. So, okay, subtract 5 over 3x minus 2. Let's just make that a bit longer. There we go. Now again, our guide here should be ordinary numbers. What do we do with ordinary numbers in arithmetic when we want to add two numbers together? Let's use a coloured pen again. So let's say we had, I don't know, let's keep it really simple. Let's say we had a half and a third. Well, what we would do is we would say, well, what's the lowest common multiple? That will give us our common denominator. Well, it would be 6. 2 times 3, in fact, gives us our lowest common multiple, so that would be 6. And what we usually do is we could separate these out and say, well, it's then, well, half would be 3/6, and a third would be 2/6, but usually we can just do this, the fraction part straight away, put the 6 underneath, and then add those together to get 5/6. Okay, well, that's the method we're going to use here as well. So let's get our ink colour back. So in other words, we're going to find a common denominator by multiplying these terms together. And then we're going to say, well, our numerator, to keep it the same, has to be multiplied by whatever it was that we're multiplying by. Now I'll show you that. I think it's much easier to show you that than to try and explain it. So let's write it out here. Equals 7 times 3x minus 2 divided by And here's our denominator. So remember, it was this multiplied by this. So it's x plus 1 multiplied by 3x minus 2. Okay, like that. 3x minus 2. Oops. Complete the bracket. So that's half of it done. Now we've got subtract minus 5. Okay. Times, well, x plus 1, because we needed to do that in order to preserve the fraction. So we have 3x minus 2 as the denominator and x plus 1. So you can see here that all we've done is rewritten. Let's have a look. Let's just change it. There we go. So we've rewritten each of these fractions, seemingly making them much more complicated, but the reason we've done that is so that we can combine them. So 7 times 3x minus 2 over x plus 1 times 3x minus 2 is no different to 7 over x plus 1, because the 3x minus 2 obviously would cancel, and if we were simplifying that, it would just go back to this. Here we've got 5 times x plus 1, and the x plus 1 is in the denominator as well, and so again that would cancel. But what we've got here is x plus 1 times 3x minus 2. We've got the same denominators, so we can now combine. Okay, we can just add these together now. So we've got this times the same thing in the denominator means we can combine the fractions. Okay, so let's do it. So now we say 7 times 3x minus 2, subtract 5x plus 1 all over the common denominator, there we go, of x plus 1 times 3x minus 2. So I hope that's clear, but if you're not clear, just pause the video or go back on previous videos actually and just check that you understand this principle of combining two fractions when we're adding them together. And there are much more complicated examples that we've shown in an earlier video. But if you're secure with that, if you understand how that works, and you're sure about how this works, let's try another one. Okay. Before we do, we just have to sort this out a little bit. So the next stage is going to be to expand out these brackets here. Now, in the denominator, I'm going to keep these here, and you'll see why in a moment. I'm going to keep these in the factorized form, because that could be useful later. But for the numerator, clearly we need to expand these brackets and combine like terms. So we'll do that like this. So we're distributing the 7 across the 3x and the minus 2 to give us 21. So 7 times 3x is 21x. 7 times the minus 2 will give us minus 14. Now the next bit, minus 5x, and then the minus 5 times the 1 gives us minus 5. And you can see why I've done that, because now we can easily combine these terms together. Let's just put the denominator in here. It's a bit of a pain, but I'm going to write this out fully. There we go. So now, combining the numerator of the terms in the numerator, we've got 21 minus 5x, so we're just commuting that over there and combining. 21 minus 5x will give us 16x, and minus 14 minus 5 will give us minus 19. And then we've got our denominator, x plus 1, 3x minus 2. And that's it. That's our answer. Now the reason why I didn't simply multiply this out is because in the numerator it might have been that this factorized. In other words, we could have, for example, taken a number out. This could have become, I mean, if that was, say, 16 and not 19, then we could have taken the 16 out and it would have been x minus 1. And that might have provided an opportunity for cancelling with one of these binomials in the denominator, which would have meant we'd simplify it. So it's a technique of just keeping these in the factorized form which can save time if there's going to be an opportunity for cancelling and simplifying. But this isn't the case here, so what I'm going to do is, let's just erase that. I'm going to, just to give myself plenty of space, I'm going to just expand out this bracket now. So I get x times 3x is going to be 3x squared. X times minus 2 is minus 2x. 1 times 3x is 3x, so it's 3x minus 2x, giving us plus x. And then 1 times minus 2 is going to be minus 2. And there's our answer. 16x minus 19 over 3x squared plus x minus 2. And it can't be simplified any further. Great. Let's try another one. Now this time, what I'm going to do is alter things. Let me show you why, so that you can understand why it is I'm doing what I'm going to do next. So here we had our variables. Let's just put an arrow. The variable x is in the denominator. Right, that's a bit scruffy, but hopefully that's clear enough to read. So the variable is in the denominator, but in the numerator we've only got, let's just draw an arrow here, we've got constants. So fixed terms, fixed values in the numerator. What would happen if we had not only variables in the denominator but also variables in the numerator? And very often in exam questions that's the sort of situation you'll find. So let's just erase these here now that you understand what it is I'm doing and why I'm doing it. Okay, so I'm going to invent a couple more fractions, similar I think to what we've got here. I don't want to go into very complex areas, although you can. But I just want to keep this simple for this tutorial so that you can see how this works. So let's call this addition 1, and now we'll work on an addition 2, addition 2. So what should we have? Let's have something like this. Let's just start with something pretty straightforward. 5 plus x over 2, and now, yeah, okay. Now I'm going to introduce another x term in the numerator. So instead of just 3, let's have 3x, and I don't know, let's have something like x minus 4 in the denominator. There we go. Okay. So again, if we think of our example of ordinary conventional numbers, conventional fractions, we would simply combine these two denominators to create a single denominator by multiplying them together. So let's do that. Okay, so let's draw our fraction bar straight away. There we go. So we've got x plus 2 times x minus 4. And this time I'm not going to write it out quite as fully as that. I think you can see the pattern. We take our x minus 4 over here and multiply it by the numerator over here. So we've got 5 times x minus 4. Add, because we're going to just add these ones. Now, 3x instead of just 3, so our numerator is 3x. And we have to multiply it now by x plus 2. And just as before, you can see what's happened here. We seem to have made this much more complicated, but the x plus 2 is here and it's there, and the x minus 4 is here and there. So I think if you work this through, you'll understand how we can do this and how useful it is, because it allows us to do the next bit. What we're going to do is keep the, let's do that straight away. We're going to keep, remember, the denominator the same. We're going to keep it in factorized form, x minus 4. But with the numerator, we're going to expand the brackets. We're going to distribute the 5 across the x minus 4 and distribute the 3x across the x plus 2. Okay, so 5 times x is 5x. 5 times minus 4 is minus 20. Now, plus 3x times x. So that's 3x squared. And 3x times 2 gives us 6x. Okay. And we haven't left ourselves enough room, so I think I'm going to go down here for this. We now need to collect like terms, so we've got 3x squared plus, so we've got a plus 5x and a plus 6x, so plus 11x minus 20 all over x plus 2 times x minus 4. Now the reason we kept the denominator in factorized form, if you remember, is because it might be that we have an opportunity for factorization in the numerator and then we can cancel. Now, it depends on whether this is factorable, and probably it isn't. Usually there isn't an opportunity for factorizing, but we ought to check, because if we can simplify this expression, then great. You know, we want to have a simplified answer if we can arrive at one. So let's use our trick with the discriminant. I'm just going to use a delta symbol here, so that just to symbolize that we're using the discriminant. The discriminant, if you remember, is b squared minus 4ac. And if you're not sure what I'm doing here, if this is all Greek to you, then please go back to the previous video where it's carefully explained. Okay, so A is 3, B is 11, and C is minus 20. So B squared is going to be 11 squared, 121, minus 4 times whatever A is 3, and C is minus 20, so minus 20. And actually, I think this is going to turn out, yes, it looks like it's going to be very interesting. So 121 minus 4, I'm going to commute this actually, so plus 4 times 20, it gives us 80. So just combining those terms, times 3, in other words, 121 plus 240, giving us, great, 361, which is a square number. You might recognize it. Good idea to learn your square numbers so that you do recognize these things. So 361 is in fact 19 squared. Okay, so that means that this numerator is in fact factorable. So, okay, let's do it. Let's see whether it produces one of those other terms, either x plus 2 or x minus 4. If it does, even better. Now, how do we factorize a quadratic expression? Well, we can do it by trial and error, but I prefer to do it systematically, and I suggest that you should too. Let's just change that back to a darker color. There we go. So what we do is we take our middle term, that's what we're going to split apart, so that's what we're looking for, so that's our sum, and we put it down here, and I'm going to then multiply out 3 times minus 20 is minus 60, and then we're looking for factors of minus 60, so to make, which will sum to 11. So I've got 1 and 60, 2 and 30, 3 and 15, 3 and 15, 3 and 20, I do apologise. So 3 20s are 60, and we're getting closer. So at this stage I'm just looking at it because we're getting closer. These are going to be the negatives, by the way, because we want a positive in the end, so these large numbers have to be positive. So the next one's going to be minus 4, and that will give us 15. And 4 times 15, or minus 4 times 15, will give us minus 60, and it will also sum to 11. So great, we've now got our way of splitting that middle term. I'm going to do a little grid down here. You don't need much space for a grid. It's really just to do a bit of working out here, see what's going on. Okay, so I'm looking for my factors to come out at the top and the bottom. I'm going to fill in what I know already. So I know 3x squared will work nicely. And I know that I'm looking for, let's put the 15x here. We're looking for 15x minus 4x, giving us our 11x there. I could put my minus 20 in here if I want. I probably don't need it. So now I can see I've got the 3 and 15 here, so I'm going to put, I'm going to put my 3x here. So there's the first term of one of my factors. And 3x times x would give us our 3x squared there. And the rest is very straightforward. 3x times 5, so there we go. X plus 5 is one of our factors. 3x plus 5 will give us 15x. And x times, well, minus 4 will give us minus 4x. So that's completed that. And now we can factorize our numerator. So instead of 3x squared plus 11x minus 20, I'm going to say is identical to, because that's a better way of putting this. I'm just factorizing this top. So I'm not really doing any calculation. I'm just expressing this in an identical way, in a way that produces, so we call it an identity because it's exactly the same. But no calculations, no manipulation going on here, just factorizing the top. So that becomes 3x minus 4 times x plus 5. Okay, so I sigh a little because sadly that hasn't given us the opportunity to cancel. Never mind. So looking now at these, at the numerator and the denominator, if I'd have had x plus 5 down here, or if I'd have had one of my factors coming out as x plus 2 or x minus 4, anyway, there's no repetition at all these binomials are different, so I'm afraid we can't do any cancelling. It might have been that we had a square coming out, a perfect square, and again that could simplify by simply taking out one of those terms and then squaring the brackets. But no opportunity for that here. Okay, but we know that, and so now we can see that there's no possibility for cancellation, and so we can't simplify this. So we've arrived finally at our answer, which we'll write out again, is identical to, let's multiply out the brackets then, 3x squared plus 11x minus 20 divided by, there we go, whatever this is when we multiply this out. So it's going to be x squared minus 4x plus 2x, so minus 2x minus 8. And there's our answer. Now, let me just show you something that hopefully clarifies what would happen if we had the x term in the numerator now and not in the denominator. What I've been working on here then is a quadratic expression that isn't factorizable. So 4x squared plus 8x minus 1. Definitely not factorizable, because if we work out what the discriminant is, that would come to, well, it'd be 64 minus 4 times 4 times minus 1. 64 plus 16 equals 80. There we go. So 80 isn't a square number, and so we know it's not factorable. But I can make it factorable by adding a fraction, an algebraic fraction, and I'll show you that now. So in the bottom left-hand corner, I've got minus half x, and I can show you that this is now factorable by working out what the sides would be. So if I have 2x and 2x here, 2x times 2x will give us our 4x squared. 8x divided by 2x will give us plus 4. So 4 times 2x gives us the 8x term here. And now, if I look at my minus 1 divided by 4 will give us minus a quarter. minus a quarter. And now just to check that this term is correct, 2x times minus a quarter is minus a half x. Okay, so the two binomials, the factored form of 4x squared plus 8x minus 1 minus a half x would be 2x plus 4 and 2x minus a quarter. So we're now going into fractions. But of course, what's happening here is we're forcing an unfactorable expression to be factorable, and we're departing from the integers. Okay, and the reason for doing that is to show you something else. What we've got, just as we had previously, is a term that now has a quadratic that usually has three terms. So we have the x squared term here, we have plus 8x, and we have the constant minus 1, and a fraction, minus half x, or x over 2, which would be the same. So there's our fraction. Now, in this case, and this is unusual, we can combine the 8x and the half x because they're both like terms. I'll show you what I mean. If I do rewrite this, let's just erase this term here and write it slightly differently. If we write it as x over 2, and this one here, so let's get our eraser, I can write as, here we go, 16, so it was 8x, so I'm going to make a common denominator, so 16 halves is the same as 8, so 16 over 2 is 8 times the x. So I've got, and I'm not sure why I changed that actually, let's change it back because it's actually made it less clear. Okay, so minus half x, there we go. Now you can see immediately now that this is just a conventional x term, and this is similarly an x term, therefore I can combine the two. Let's put it over here. I can collect my like terms, so I've got 4x squared plus, well, 16 halves and another half, subtract a half will give us 15 halves, 15 over 2 times x minus 1. So we're back to a three-term quadratic. So that's what happens if the fraction happens to have only the, in fact it probably is a good idea to write it the other way now. So if you get something like this, if you get a fraction with an x term, in other words the variable in the numerator, and nothing except an ordinary number in the denominator, so no variables in the denominator, then you can collect like terms. But if you get something like, well, let's have 3x squared plus, let's say, well, it doesn't really matter, 7x plus, let's say 2, then we're not going to be able to gather like terms. And what I want to do is I'm going to show you exactly why. So let's add a fraction with, let's add a really simple algebraic fraction, 1 over x. So in other words, a fraction where the variable is in the denominator and just a number in the numerator, just 1. Okay, now why can't I combine that with the 7x? Well, there's several ways of understanding this, but one way is just to convert everything into powers of x. So we can do that like this. We can say this is identical to 3x squared plus 7x to the power 1. Okay, to make it clear what's going on here. What we've got, in fact, are descending, let's just draw an arrow here in a different colour. So we've got descending powers of x. So as we go in this direction, our powers of x go down by 1 each time. So, okay, what happens next? Well, what happens next is we have this 2, which we could express as 2x to the power 0, because that's basically what we've got. So the x squared to the x to the power 1 is now to the x to the power 0, but anything to the power 0 is 1. So 1 times 2 is simply 2. Okay? Now what happens? Well, just as in the conventional numbering system that we have, the base 10 system, which is so we get 10 to the power 0, 10 to the power 1, 10 squared, and so on. If we go down into what with conventional numbers is the decimals, after the decimal point, we get the x term to the minus 1. So we say the next term is x to the minus 1. And x to the minus 1 is in fact 1 over x. It's the reciprocal of x. Okay? So we might well have other terms going down here. We might well have an x to the minus 2 as well in our fractions. But they're, as it were, below the decimal point, which means they're not like terms, which means we do have to express it like that. So we cannot simplify any further an expression like this. Okay.